Good evening, all of you. My name is Anil Yadav. Uh, Today is the second tutorial on fundamentals of micro and nanofabrication technology. So I am following Professor Sushuvan Avasthi's lectures from IISc Bangalore. So today, in the previous session, we have seen various technologies like additive and subtractive processes, so that are useful for micro and nano fabrication. So today we will be dealing with some defects and diffusion process. So here, so based on the dimensionality, defects are of four types. So a zero dimensional, one dimensional, two dimensional, and three dimensional. Zero dimensional are kind of the point defects, which are related to the atomic lattice points. Okay, there are these defects are kind of vacancies. If a lattice point is missing from its, if an atom is missing from its lattice point, so then it creates a vacancy of that atom in the crystal. So this is the vacancy. There is a vacancy of that atom in the crystal. So, and another is impurity. Impurity is a oh, uh, whatever crystal you have. So other than that, other than the atoms, other than that crystal elements, so there are some other elements like in silicon there are oxygen, hydrogen, or boron, aluminium, any atom which are of other foreign elements are there. So these may be substitutional or interstitial. The impurities, if it is substituting the lattice at points, atoms from the lattice points, so then it is a substitutional impurity. And interstitials are if it is other than the lattice points, there are vacancies. There are not the vacancy, there are voids inside a crystalline structure. So if these impurities sits there, then these are the interstitial positions. Schottky and Frankel defects generally come in the ionic crystals that we will see. And 1D defects are kind of dislocations. Dislocations are if a line of atoms is missing from its lattice points. So okay, so from the crystalline structure, then there comes a dislocation. A one-dimensional dislocation is there, and two-dimensional is like a sheet of atom is not present, like four or more than four atoms are not present, then it comes a two-dimensional defects. Like there is a surface, because of the dangling bonds there are surface defects, and because of this lattice mismatch, when there is a growth of a other material or a crystal structure, crystalline material, another material like growth of germanium or gallium arsenide or silicon, then it at the interface there are 2D defects because of the lattice mismatch or anything. And then comes the 3D defect. 3D defects are nothing but if there is an accumulation of foreign atoms inside a crystalline structure, then there comes a 3D defect that we will see into. And now let's see the vacancies and impurities. In vacancies, vacancy is nothing but a missing of an atom from its lattice point. This is a crystalline structure of an atom. This is crystalline structure of any piece of material. So if the atom is missing from a crystal from the crystal lattice, from its lattice points, so there will be a vacancy. Okay, then another thing is the interstitial, self-interstitial is like if this the missing atom sits at the interstitial position, it it sits in the interstitial position, then there is a self-interstitial kind of defect, which forms a compressive stress over these atoms. Okay, so These are the self-interstitial. And then comes the interstitial impurity. Interstitial impurity, first let's come on the impurity. Impurity other than these lattice atoms. These lattice atoms, you can say, uh, this is a silicon. Other than silicon, if there comes any other atom like oxygen, let us say this is the oxygen or germanium. Okay, this oxygen atom sits at the interstitial position in the crystalline structure, then it's a interstitial impurity, and it forms a tensile stress over this kind of compressive stress over the other atoms in the lattice structure, in the crystal structure, sorry. So, and then comes a substitutional impurity. In substitutional impurity, what happens is this substitutional impurity, the, when a foreign atom in the sense, whatever, other than silicon, this atom replaces the silicon from its lattice points. Okay, from its lattice point, then this is a substitutional impurity. Let me wait. Okay. Now, it is interstitials and substitution. Interstitials are nothing that, as we have discussed, these are the voids inside a crystal structure, and in these voids, the other elements other than silicon can go inside and just move randomly. Okay, these are the interstitials. And substitutions, when a silicon is, let us say, uh, this this is germanium, red one, and these are the silicon atoms of in a crystal structure, and this silicon is replaced by the germanium, then this is a substitution. Okay, why these are important? Because these are important because there is a very much effect on the electrical properties because of the substitution and the interstitials. Okay, and then comes the 3D defect. This is the like precipitate of the oxygen inside the silicon crystals. Okay, so this is the precipitation of oxygen inside. Okay, oxygen forms a cluster inside the silicon crystal. So this forms a 3D defect. So now comes the SiO2. So this is the TEM image. Okay, TEM image of SiSiO2. Okay, so this is a crystalline structure of Si. This is crystalline structure of Si. Over this Si was grown, maybe some CVD kind of technique. Okay, this Si was grown kind of CVD technique or something. So it forms because of the oxygen in over there. So it forms a SiO2 inside the silicon lattice. Okay, inside the silicon crystal, it SiO2 is formed because of some anything it can be formed. Okay, what I want to show is this is the 3D kind of defect inside a crystal structure. Okay, so as you can see, this is amorphous in nature and this is crystalline in nature. Okay, Si and SiO2. Yes. Now the another type of defect is the point defects, 0D defects, which are the Schottky defect and the Frankel defect. Frankel defect and Schottky defects generally are in the ionic crystals. Okay, so in Schottky defect, when a cation and anion are misplaced in a pair, okay, one anion and one cation are these two atoms are misplaced from the lattice points in pair. So then these kind of defects comes when the size of the both of the ionic uh, atoms, both of the atoms have small in size, like KBr and ACl. And these the size of these atoms are comparable as well. Okay, so in these kind of ionic solids, ionic crystals, these Shortcurie kind of defects can be formed. And in Frankel defects, what happens is either cation or anion is misplaced from its lattice position and it sits in the interstitial position like this. Okay, so then these Frankel defects come. So these kind of defects generally come in large anions and small cations. In these, small cation goes at the interstitial position because it is very much possible for the cation to move because of its small size through the interstitials. So it will move, it will go and sit at the interstitial position. Now, thermodynamics of intrinsic vacancy formation. So why? So that we will see why these vacancies are important for the diffusion process. Okay, so we need for diffusion, for substitutional diffusion kind of process, we need vacancies. So these, and how many vacancies are there at room temperature, at any temperature, that we quantitatively will see. So how this depends. So let us say this is a crystal structure with very less disorder. Okay, in this one it is shown a completely ordered crystal structure, and when there is no vacancy. So if we provide some energy to this one externally and it forms a there is a vacancy is created. Okay, so delta HF energy we have provided and there is a creation of the vacancy, and this system is less disordered, is more disordered. Okay, less ordered and more disordered. So if we know that Gibbs free energy should be least for a system to be stable. Okay, so delta G is equal to delta H minus T delta S. So this T delta S is nothing but the conformational entropy. So as we increase the temperature, this conformational entropy increases and Gibbs free energy decreases. Okay, Gibbs free energy decreases as we increase. Also delta H increases. So there will be a point that will so delta G. So delta G will delta G versus vacancy. So there will come a point when this is this energy delta G will be least. Okay, so at this point this is the maximum vacancy concentration. Okay, this is the maximum vacancy concentration which is given by this. N is directly proportional to exponential of delta HF by KT minus of delta HF by KT. Okay, so these are the, and exponentially depends on the temperature. Okay, as we increase the temperature, N will increase. Okay, so these are important for substitutional diffusion that we will see. So now comes the dislocations as dislocation, screw dislocation. These are kind of 1D defects. Okay, as you can see, these in this case the atoms in this line, okay, in this line are not bonded to any other atom. Okay, are bonded to three other atoms. Okay, but there is a missing point. Okay, this, because of that there is a force that these atoms will feel. Okay, that can be compressive or tensile kind of strength they can feel. Okay, so now and another is the screw kind of screw dislocation. So it's like if you are moving in this one, so you will go up, but there is a difference from an atom layer difference. Okay, but while going through this direction you won't feel any change. Okay, but while completing a single cycle or single rotation, you will feel that there is an atomic difference. Okay, this is the screw dislocation kind of that comes while twisting an a material, and at this that time it comes, and these kind of comes when you just pull or push a material. Okay, and dislocation dislocation example here this is the real life TEM image of strontium titanate, and this is the simulated image of the strontium titanate, and by this is the merged image of strontium titanate and HRTEM image, and this simulated image. So here you can see this at this position. If you want to see, there is a gap. Okay, that you can just see the atoms are very a bit sparse here. Okay, and because there is a line of atoms is missing somewhere here. Okay, if you see closely you can find somewhere here. So that so from because there will be you will see that there is a difference between the lines, the length of lines here. So you can easily point out after taking the TEM image of this of the material. Okay, so there are various defects like point defect, vacancy defects, point defects, line defects, planar defect, volume defect. There are many defects. Okay, so what we are mainly focusing on the on point defects for doping purpose through the diffusion or ion implantation, and the vacancy, because vacancy is the misplacement of any atom from its lattice points. Okay. Now let's come on the diffusion process. Okay, at the very first place, why diffusion is required? Because whenever we diffusion, okay, we will see. So first we will see the doping. Okay, we dope the semiconductor material through various processes like doping. When initially when we form the ingot for silicon wafers, at that time also we can dope the semiconductor. Doping is addition of the foreign elements in a semiconductor. Okay, so why do we do that? Because in semiconductors, what is the semiconductor is useful because we can tune the properties of the semiconductor. We can tune the conductivity of the semiconductor by adding the dopants. Okay, we can tune the conductivity. That is why it is important. The semiconductor is important. Okay, so in this one what happens is let us say these are group 3 elements, these are group 4 elements, these are group 5 elements. Okay, in these group 4 elements, these are, let us say, silicon or germanium. We take the crystal of silicon or germanium. In silicon this is the crystal of the silicon, pictorial representation of the crystal. So in this one, silicon atom is bonded to 4 other silicon atoms to satisfy its valency of the 8. Okay, so it bonds the nearby silicon with this silicon, and there will by sharing one electron with the other silicon. Okay, so that forms a covalent bond, single covalent bond. Okay, now what if instead of this silicon, if we substitute this silicon with antimony is group 5 element. Okay, Antimony is group 5 element which has 5 electrons in its valency. These have 3 electrons in the valency shell. Okay, group 3 has 3 electrons, group 4 has 4 electrons in valency shell, group 5 has 5 electrons in the valency shell. Okay, so in this one, if we replace this silicon, the middle silicon or any this silicon with the group 5 elements, so the 4 electrons of the antimony will be bonded, will be shared with 4 nearby silicon atoms, but one electron will be there with will still be there in the valency shell, which is not bonded to any other silicon atom. Okay, this electron is very loosely bound to the antimony and it is free to move in the crystal. Okay, in the crystal it is free to move, it is very loosely bound. So we have created an extra electron in the lattice in the crystal by doping the semiconductor, by doping the silicon crystal. So this extra electron will contribute to improve the to change the conductivity of the lattice. So this is done by doping of the antimony. Okay, this is how we can tune the conductivity of the semiconductor. Now let us say, instead of this silicon, now if we dope it with group 3 elements, okay, let us say with the boron. So boron has 3 electrons in its valency shell, so 3 of the electrons will be bonded to, will be shared with the 3 other silicon atoms, but there is no electron left for the 4th silicon atom to be shared. So there will be only one silicon atom that one electron from the silicon that will be shared, but there will be a hole. Okay, there will be a deficiency of the electron is the hole only. Okay, deficiency of electron is hole which is positively charged, we can say. Okay, so there will be hole, so this will create a p type of semiconductor because of the p positive kind of we can say charge here. Okay, which is loosely bound to this boron atom. Okay, so it is also free to move inside the lattice. Okay, so this is why doping is important. So now let us come on the p-n junction. So in the previous session we have seen some while making the silicon wafers, I told you that these wafers or crystals can be doped with any boron and can be doped with any impurity. These dopants are nothing but the impurities only. Okay, that can be done at the very first stage when we make the ingot. Okay, if we add some the impurities in liquid over there itself, in the melt itself, so we can dope the semiconductor. But why do we need the doping through diffusion or ion implantation? Okay, that we will see. So do you know how the p-n junction is nothing but a p-type semiconductor, n-type semiconductor. When they are put close together, so there will be a movement of electrons from the n region and movement of holes to the p region. So there is this kind of diffusion happens, and a depletion layer formation happens because of that. And this is the Venn diagram of the p-n junction. Okay, and this p-n junction has many applications in devices. Okay, so this fabrication of the p-n junction requires the diffusion or ion implantation. So we cannot make just a p type of silicon and n type of silicon, and we cannot stick these together. That won't work. Okay, so fabrication of PN junction, what happens now? So these can be done in two ways. One is just take the N type of the silicon wafer, do the epitaxial deposition through CVD kind of process over the N type silicon. So there will be a PN junction. Okay, there will be a PN junction. Now, and another method is dopant diffusion. Okay, dopant diffusion can be done through two methods. Uh, one is diffusion and another is ion implantation. Okay, so in this one, what happens is we diffuse the dopants or impurities inside the silicon wafer at higher temperatures. So it will form it these impurities. If we keep the impurities over the substrate, and they will diffuse down inside the lattice. Okay, so it will form at this position. This will form a p type of the silicon, and there this is the junction, PN junction. Okay, so as I told you, there are various type of defects: point defect, line defect, volume defect, and planar defect. But what we are interested in, the for diffusion process or ion implantation process, we are interested in point defects only. Okay, for the doping we are interested in this one. So there are other things also: interstitial impurity, substitutional impurity, and vacancies. So these are important: interstitial, substitution, and vacancy. So these are correlated, these two, substitutional impurity and vacancy. So whenever there is a vacancy, then there is a substitutional impurity, or this substitutional impurity diffuses through the vacancy only. Okay, so that we will see in this diffusion mechanism. So there are two things: one is interstitial diffusion and another is substitutional diffusion. In interstitial diffusion, the impurity atom, the impurities can be oxygen, nitrogen, germanium, aluminium, gold, can be any. That these kind of these atoms diffuse through the silicon crystal, diffuse inside the silicon crystal through interstitial position. Interstitial positions are the voids. These are the voids inside the crystal lattice. Okay, inside the crystal. Okay, so these are these move very fast because they do not need vacancies. Okay, they do not need a vacancy. Vacancy is that thing which is the missing of the silicon atom from the lattice point. Okay, so here low activation energy is required because there is no breaking and formation of bond at this. So in this one, whenever there is a substitution, there is a formation of bond and breaking of bond is happening over there. So that is why. So hydrogen, metals, and oxygen, any these kind of are atoms are of small size, and they can diffuse easily, very easily through the silicon. Okay, interstitial positions. So in substitutional diffusion is so they needs vacancy, and these are slower because whenever they moves, this impurity atom will go to this vacancy, and it will wait for the vacancies to be created nearby. Okay, whenever there is a nearby vacancy, then this atom after the movement at this position, it can move here, but wherever it finds the vacancy. Okay, so that is why the vacancy is important for the diffusion mechanism. Okay, so through diffusion process, through substitutional diffusion process, the atoms which are of of similar size or comparable size of the silicon, they diffuses through the substitutional mechanism. Okay. They require high activation energy because there is always a breaking and formation of bond at whenever there is a vacancy is created. Okay. Now there is now let's substitutional and interstitial diffusion that we have already seen. So here is the vacancy, here is the vacancy, here is the vacancy. These are the vacancies, and this is the impurity atom. This impurity atom will move at this location, and after that, this there is a vacancy is created over there. So some, let us say this atom may move at this position, and after this atom, the impurity atom will take the position of vacancy. Okay, these so this is how the impurity impurity atom moves through the substitutional diffusion. Okay, so, and in interstitial diffusion the atoms are very small. The impurity atoms are very small. They can move easily through the interstitial positions. Okay, through the interstitials. So these can move easily. So now, so the requirement for the interstitial diffusion is it should be the impurity size should be small. Okay, these are the kind of the impurity atoms which moves through the interstitial diffusion, and these are the atoms which are of similar size of the silicon. They move through the substitutional diffusion method. Okay. Now we need for the mathematical outline. So how the diffusion, how much the diffusion has happened inside a lattice, inside a crystal, so that we will see through the fixed law of diffusion. The fixed law says, so if let us say there is a single particle and this is the wall. So if this is the single particle which is moving randomly, okay, inside this box, and if we remove this wall, if we remove this, so this particle may come or may not come. So but we do not know, because this is a single particle inside a big box. So it is not feeling any pressure or anything. Okay, so if we are taking an ensemble of particles, okay, in ensemble of particles, so if we remove this, slowly the concentration of particles will also be same over here after some time. Okay, so initially it will be a lower concentration. After some time it will be at the same concentration in the full box. Okay, so if we take a very very large number of particles, so we can predict the movement of these particles, the concentration of these particles in this box with the time. Okay, in this box with the time, so that we will see. Okay, so now flux of particles through across an area A. This is the area A. Okay, cross sectional area A. If the particles are coming, okay, flux of the particles depends on the gradient of the concentration. Okay, so gradient of concentration is, let us say, so this is the concentration of the particles and this is the x direction. Okay, so this is the box, let us say, and box, or what we can say, the crystal of any element. Okay, crystal of silicon crystal. Okay, so let us say the impurity atom, let us say boron is the concentration of boron inside this silicon is follows this line. So concentration is higher at this end, concentration is lower at this position. So what will happen is uh, these boron atoms will diffuse from higher concentration to the lower concentration. Okay, they will diffuse from higher concentration to lower concentration, and flux of particles crossing an area, crossing this area at this position, this area crossing, so that depends on the gradient of the concentration, that depends on the gradient of this is the gradient is the slope of this at this position. Okay, slope of this at this position. So this flux J, number of particles crossing an area per unit time. Okay, that is the flux, number of particles crossing an area per unit time. So that is the flux, which is given by diffusion coefficient minus of the diffusion coefficient and del C by del X. This is the gradient, that depends on the concentration gradient. How much concentration is here, how much concentration is there, minus divided by X, that is the gradient. Okay, so it is very similar to the carrier diffusion if you have studied the semiconductor device physics. So in that there is a diffusion of carriers from higher concentration to the lower concentration in the PN junction or in any kind of junction. You can see that. So mainly PN junction is the base for every most of the devices. So if you get the expertise in the PN junction, you can solve most of the device physics. Okay, so here the negative sign is because of the atoms are moving from the higher concentration, higher at this concentration to the lower concentration. That is why there is a negative sign. So now let us see the fixed second law. In fixed second law, as we have seen, okay, the constant. Okay, let us see. This is the 1D solid, okay, of silicon. So let us see at any random position. This is the dx. Let us take a dx thick of this solid. So there will be a flux from left to right, and which is going inside this dx thick area, and jx plus dx is coming out. Okay, the flux in and flux out. This is flux in and this is flux out from the dx region of the area. Okay, so the concentration cxt, the change in the concentration cxt, okay, the change in concentration with the time, rate of increase of the concentration with the time, okay, that is given by the flux, change in flux. Okay, change in flux at this point, change in flux at this point. Okay, which is given by jx minus j of x plus dx, dc by dt into dx. So from here you can see dc by dt, del c by del t is equal to del j by del x. Okay, so from let us put the first law from the fixed first law. So we can rewrite it, d del c by del t is equal to del by del x of minus d of del c by del x. Okay, so now open another thing is this concentration. C is nothing but the concentration and d is the diffusion coefficient. Okay, so this diffusion coefficient depends on the concentration. Okay, if the higher the concentration, this concentration will influence d, diffusion coefficient, but most of the time it is constant only, which is independent of C. Okay, but that this D depends on temperature and several other factors. So del C by del T is given by minus D of del 2C by del X square, which is the fixed second. So this is a second order differential equation, which is not that trivial to solve. So for this we need one initial condition in time and two boundary condition in space. Okay, we will see for our purpose, for our diffusion purpose, which cases are important, that we will look into. Now let us take the infinite source. Infinite source is I will tell you. So this is the silicon. Okay, this is the silicon. So we have kept the dopant at this position on the top of the silicon wafer. It is tilted in by 90 degree in the left side. So this is the silicon. So we have kept a dopant over, and this source, this dopant source, is infinite. It does not change with time. The concentration of this dopant is not changing with the time. So that's why we are saying it's an infinite source of dopant is there. So infinite source of dopant. Surface concentration is fixed. We have fixed the surface concentration. Depends on the solid solubility. Okay, so now we will see. So if we keep the dopant over silicon, so let us see, this is the silicon wafer, and over it we have kept some dopants. Okay, over this we have kept some dopants. So if we raise the temperature, what will happen is these dopants will diffuse inside. Okay, so how much the dopants can diffuse inside at the surface is limited by the solid solubility, CS. Okay, solid solubility of the dopant in the in silicon crystal. Okay, so it is limited by this one. So maximum concentration that can be inside a silicon of that dopant is CS. It cannot go beyond that. Okay, so we have fixed the concentration of CS, so by giving an infinite source. Okay, so CS is fixed, so we have fixed the boundary condition. Okay, CS is fixed, we have fixed the boundary condition at x is equal to 0, concentration C is equal to CS. This is the boundary condition. Okay, for all time. And another thing is, so this is C is equal to infinite, x is equal to infinite at this position. So we have normalized, this is the normalized one. So x is equal to infinite at this position. So we are assuming that C infinite into or T at any time the concentration is equal to 0. So the no dopants are not reaching at the end of the wafer or at the end of the silicon. Okay, till at this point no dopant is reaching. So we are assuming that this is the infinite, x is equal to infinite we are saying, because the wafer is too much thick for the dopants to reach till the end. Okay, we are assuming this, the thickness is high, this silicon thickness is x is very high. Okay, this is the another boundary condition. Okay, and initial condition that we have seen is at T is equal to 0 there is no dopant is inside the silicon. At T is equal to 0, as we can see. Okay, wait. At T is equal to 0, dopants, there is no diffusion of any dopant, so this, there is nothing inside the silicon. Okay, so after putting these boundary conditions in the previous one, this one, so we will get the solution like an error function solution to that differential equation. Okay, so this concentration, this is space time equation of dopant concentration. ठीक है, dopant concentration, space time equation. So what we will see is now, okay, Now what we want so if you solve this equation, if you plot the equation with the time at any for any time t is equal to t1, if you plot this one, this one is for t is equal to t1. Okay, so t is equal to t1. So this kind of graph you will get. Okay, at this is the normalized one, so maximum concentration at 0, that at 0 can be cs. Okay, cs by cs is equal to 1, c of xt by cs is, this is the normalized one, so the graph will look like this. Okay, this is the space time, this is the concentration for at any time t after the diffusion starts at t is equal to 0 and t is equal to t1, let us say 15 minutes. After 15 minutes, how much dopant is diffused, okay, inside the silicon crystal? So that is this given by this graph. At this position this much of dopant is there, at this much of position, at this position this much of dopant concentration is there. So this is what, okay, so if we increase, and that is given by this error function. Okay, if you increase the time, you will get the, it will be increased if you get increase the time. Okay, and now another thing is the is uh, is the dose. Dose is nothing but how much impurity is there inside the silicon. Okay, that is the dose. Okay, how much impurity is there, so that is given by the area under this curve. Okay, the area under this curve is nothing but qt is the dose, and which is given by the area taking the integral of that error function. Okay, so this is the dose, so we can calculate the area under the diffusion profile, and this will this is given by 2 by square root of pi cs square root of dt. The dose is nothing but how much material, how much dopant is going inside. So if we want to increase the dopant concentration inside the inside the what to say, the crystal, so what we will do is we will increase the time. Okay, so that is qt is given by this one, so this is the graph, so this is, and area under this graph is qt. If we want to increase the area, and we want to that is ultimately we are increasing the dose. Okay, so that is given by 1.13 cs square root of dt. Okay, so if we want to increase the dose, or we want to increase the concentration, dopant concentration, what we will do, we will increase the time. Okay, we can increase the diffusion coefficient. Okay, diffusivity. So this is a very weak dependent on time t, square root of t. If you have a silicon wafer, so you want to diffuse boron, so for 1 micron it takes 15 minutes. Okay, or let us say for 1 micron it takes 4 hours. Okay, for 1 micron of diffusion it takes 4 hours, but for 2 micrometer of diffusion it will take 16 hours. Okay, that is what I want to say, because it is too much time consuming, and which is not feasible. Okay, which is not feasible that much. Now what you can see is another method is in increasing the diffusivity, that we will see on. Okay, now let us see the solid solubility and diffusion. Solid solubility is the maximum concentration that can be there of the dopant that can be there inside the semiconductor or inside that crystal. Okay, so these are the atoms, atomic concentration, and which we can say the solid solubility, and with the temperature how this solid solubility is changing. Okay, so this is the solid solubility, and this solid solubility is function of the atomic sizes. Okay, the relative atomic sizes of the material, of atomic sizes of the dopant and the crystal. Okay, and better the lattice match and more is the solubility. Okay, better the lattice match, that we will see in the misfit ratio in the subsequent slides. So that misfit ratio will tell you about the lattice matching. Okay, the ratio of the impurity to the ratio of the crystal, so crystal point. Okay, now let us come on the doping and electrically active. So whatever you dope, that doesn't mean that will contribute to the doping. Okay, that if whatever impurity you are putting inside the crystal, that doesn't mean that will act as a dopant, or that will act, that is electrically active. Electrically active in the sense that will contribute to the improve the concentration of the electrons or concentration of holes to tune the conductivity. That doesn't mean that. Okay, so okay, in electrically active in the sense, so if you are doping a semiconductor with this is arsenic and this is phosphorus. If you are doping with arsenic, let us say with arsenic you are doping, so what will happen is this is the dopant concentration. This is nothing but it is same that of the solid solubility line. Okay, and how much the electrically active, that is around a order less than that of the doping that you have done. Okay, if you are doping with 1000 atoms of arsenic, only 100 atoms around will contribute, 100 or 200 atoms of arsenic will contribute to the electrical conductivity. Okay, this is the thing. If you, that's why if you increase 10 raised to power of 15 of the doping that you have done, but only 10 raised to power 14 of the atoms of the dopant, they will be electrically active. So you need to take care of that as well. So how much you are tuning the conductivity. Okay, then now comes a finite source for the diffusion. So in this one, this your dose, this is your dose, nothing but this is your dose, and this is fixed. Okay, the dopant is fixed, that is not changing with time. Okay, this is fixed. So now the same thing, now what you can see is this is silicon. Okay, this is silicon, and at t is equal to 0, and at cxt, cx0 is equal to 0. This is the thing, that at 0 time is equal to 0, there is no concentration of the dopant inside the silicon is 0. So this is the initial condition. Okay, now boundary conditions. C infinite, let us say at this position, again we are assuming that silicon is very thick, so at this position, at this concentration is 0. And another is at 0 to infinite, Cx is equal to 0 to infinite Cxt dt at any time t, okay, is given by this area. This area is nothing but this area is nothing but dose, so this dose is constant. Okay, these are two boundary conditions. This is the initial condition. If we If we solve the differential equation with these three conditions, then we will get this kind of solution. Okay. So what we call it, I forgot the name, so what we call it, okay, whatever. So this kind of solution you will get. Okay, so now what we can see is this is the finite source and this is the dose. So you can calculate that if we increase the time. Okay, so what will happen is, so if we increase the time, this is the curve for t is equal to t1. If we increase the time to t2, t2 is greater than t1, so what will happen is this will fall and it will be like this. Okay, it will be like this because this concentration has moved towards this. Okay, but the area will be same. The area under the curve will remain constant. Whatever will happen, this area, the yellow curve under yellow and curve under the area under the curve gray curve will be same. Okay, that won't change because the dose is same. Okay, so now this okay, this is the infinite source versus finite source of diffusion. So this is the infinite source, these are the infinite source, and one more thing, C by Cs with time, what is with the time this is increasing source. This is Ariel function, this is Gaussian, this is Gaussian, this is okay. These two are of infinite sources, but what is the difference? We have given enough time. So that I need to see once. But these are the infinite sources, that is the error function. But this looks like a Gaussian kind of curve. This is the Gaussian, this is the error function only. But what is the difference between these two? That I'll come on in this next time. So now let us say, so there are two ways to improve the diffusion. One is the diffusivity, one is the time. So how to increase the concentration of the dopant inside the crystal. Okay, and so that depends square root of dt. Okay, so now the diffusion coefficient is a strong dependence on the temperature. It strongly depends on the temperature. As we increase the temperature, the diffusion coefficient increases. So that's why we do these at higher temperatures. Okay, diffusivity varies with temperature, and this E is the activation energy. Okay, so this is kind of a Arrhenius kind of plot is there in the this is the log plot. Okay, log plot of the diffusion coefficient, and with the temperature it is varying like this. So at higher temperatures the diffusion coefficient is higher. So this is interstitial, this is substitutional. For our diffusion we need substitutional diffusion. So because of interstitials does not count in the do not count in the electrically active. Okay, so you want substitutional diffusion. So diffusivity, this is the diffusivity, interstitial diffusers and the dopants. Okay, so interstitial diffuses faster than the dopants. Okay, so this is what. So how uh, the diffusion uh, happens? What is the what kind of tool that you can use? What kind of the of machines that you can use? Okay, machine in the sense, machine is different thing, but you can say the tool. Okay, so dopant source for that. Okay, this is a dopant source and schematic of for the diffusion. Okay, so there are different type of dopant sources. So one is a gaseous dopant, solid dopant, or liquid dopant. So we will look into these, how you can use these dopant sources for the diffusion of the silicon wafers. Okay, so there are in dopant gases are for boron doping, diborane is there, arsine is there for n-type doping, and phosgene is there, phosphine we can say, or phosgene. So these gases are very highly poisonous and highly dangerous. So these kind of diffusion or these kind of gases are used with very care. And another sources are solid sources, boron nitride and arsenic oxide, phosphorus oxide, and the liquid sources are also, which are halides. Okay, halide. So what do you need for this one? You need a chamber. Okay, you need a chamber and one impurity. Okay, so we the impurity gas, we open, there will be a wall, we open the wall, we open this wall, we mix these gases, and this is the carrier gas. This will take this impurity gas towards these wafers, and there will be, this is the quartz carrier, because quartz can withstand at the higher temperatures. Okay, and this is the diffusion tube. So you can create a environment of this impurity gas. That impurity gas inside this chamber will help for the diffusion of that impurities inside the wafer. Okay, this is the thing. So now you can design your own furnace for these kind of diffusion processes, but in utmost care is should be taken care before, because these gases or these sources for the diffusion are highly poisonous and are not very easy to handle. Okay, so let us say so uh, if you have a solid source. Okay, this is for the solid source one. If you can keep your solid source in a quartz or in a in a beaker kind of, or or crucible. This, you can say this is a crucible. Okay, which we can withstand at for the higher temperatures. Okay, this is a platinum source board. This is made up of platinum, because platinum can withstand at the higher temperatures more than 1200 degrees. Okay, so here comes the nitrogen gas and oxygen gas. Okay, this oxygen will this is arsenic source. Okay, this arsenic source will be oxidized by this oxygen, and this nitrogen will take care of the out diffusion of these gaseous. Okay, so this will be converted into arsenic, arsenic oxide was already there. So this will form an oxide layer over the surface. Okay, this will form an oxide layer over the surface, and which will allow the diffusion of the boron atom inside the silicon crystals. Okay, the another method is, because in this case what will happen is these wafers which are in front will see more diffusion, and these wafers will see less diffusion. So that is why we can change the schematic a bit, so for the design a bit. So what we can do is we can take a boron nitride here, silicon, boron nitride, silicon. Alternatively, we can place the source and substrate. So in this one, the gas will take care of the out diffusion of the whatever is there in the gaseous, and that these wafers will get diffusion at the higher temperatures. From here, this boron will go, and the boron oxide will be there. B2O3 will be formed over the silicon. Okay, so that will this oxide formation of oxide over the silicon will help in the diffusion of the boron. Okay, so now a liquid source. In the liquid source, there are several designs that you can see. So in this one, what you can see, there is a nitrogen. A nitrogen is nothing but it is a carrier gas. So if we flow the nitrogen if we bubble this nitrogen through the liquid source, okay, this is the liquid source, whatever can be the POCl3 is there. Okay, this POCl3 is there, so that will go through this. Okay, we open this wall, this POCl3 will be there, and there is oxygen is also coming, that will form P2O5. Okay, that P2O5 will be deposited over the silicon. Okay, this P2O5 will be deposited over the silicon, and that will form P and PSiO2. Okay, this phosphorus will diffuse inside the silicon. Okay, and whatever the byproduct or unreacted POCl3 will be taken out through this nitrogen, with the nitrogen, and so we will treat the gas before the exhaust, so that it should not harm the environment as well. Okay, so there is a gas source that is the same thing. Dopant gas is going, and nitrogen is going again. It will form oxygen is also there, that will form B2O3 over there, and this B2O3 will be deposited over the substrates, and there will be a diffusion of boron inside. Okay, that is the thing. So now comes the misfit ratio. Okay, so how the rate depends on the misfit ratio. Okay, so if the misfit ratio is nothing but the radius of the dopant atom to the ratio of the radius of the dopant atom to the radius of the silicon atom. Okay, if the ratio, this misfit ratio is lesser, if this misfit ratio is less, then the size of the dopant atom is lesser. Okay, if the misfit ratio is high, the size of the dopant atom is more. Okay, in this case what happens is this if the size is less, that can go, there is a diffusion rate is very high, because it can go through the interstitials as well, that we have studied. Because interstitials, for the interstitial diffusion, there is a very less size of the atom can go through the interstitial positions very well. So this is the thing. So more higher is the size, more is the size of the dopant atom, the diffusion is very slow. Okay, very low diffusion is there, but at low diffusion rates you can control the diffusion amount of the diffusion for the silicon. Okay, so you can actually control, you can have a very good control over the diffusion. Okay, so now these are the additive process. Okay, So now let us see another point on field enhanced diffusion. In field enhanced diffusion, what happens is, in field enhanced diffusion, so when we you dope with the boron, okay, let us see the boron with silicon. So this is the diffusion profile, okay, this is the concentration profile of with the distance, okay. So boron creates an hole, okay, and hole uh, with the hole diffuses faster than the atom, okay. These holes inside this silicon, they will diffuse faster, and the whole profile will be this orange dotted line, and the electron this boron B negative profile will be this. So there will be excess electrons in this position, excess holes in this position, so there will be an electric field. So this electric field will pull the boron atoms this direction, okay. So with higher the concentration, that's what we were saying, with higher the concentration, the this the diffusion coefficient will be modulated, and this diffusion coefficient will be more than expected, okay. So this is the enhancement factor, and this is the enhancement factor, and this is the total diffusion, effective diffusion, because of the electric field which is induced because of the doping only, okay. Now the field enhanced diffusion, so initially you have taken a p type of silicon wafer with the doping concentration this 10 raised to power 17. Now after the ion implantation, this is kind of the ion implantation only, this is the after ion implantation of n type carriers, n type dopants. So and this is the electric uh, diffusion with the electric field. So after that, what happened is, because of the electrons and holes, no, because of the electrons and the dopant, positively charged dopants actually, so they disturbed the p-type doping concentration, okay. They disturbed the p-type doping concentration because of the electric field that is created because of the n-type dopants, okay. This is the thing. So that's it for the today. So if you have any question, you can write to me, or you can write on the form, we will solve them, okay. Thank you, we'll see you again.